Hello and welcome to another power system analysis class. In the previous class, we started bus systems and flow and flow direction and flow tie systems and how we connect different bus systems. Today, we're going to speak about generator costs and generation costs and also the electricity pricing and which factors actually affect electricity pricing. It's not just generator costs. We also have costs associated with transmission as well. So what is a generator cost? When producing electricity, we have many fixed and also variable costs associated with power system operations. Some systems have higher initial costs, like nuclear or hydro, but their operation cost is lower. Other systems have lower initial capital costs. The CapEx or capital cost is lower, but the OpEx, which is operational cost, is higher. An example of a system that requires a lower or smaller initial capital cost is going to be gas and coal power plants. They're much cheaper. So let me give you an example. For 1 GWh, 1 GW system for a gas, it's going to be $200-300 million, and it takes roughly 1 to 2 years, 2 years now. But if you want to build the same nuclear power plant, it costs $5-6 billion, and sometimes even more. And at least it takes a decade now. But gas, you don't know what the price of gas is going to be, but nuclear, you have a better idea. And gas power plants lifespan is shorter than a nuclear power plant. We have nuclear power plants that are like half a century old right now. But the problem with gas is the cost of operating it because of the fuel cost is higher than nuclear power plant. So the recovery of the investment is faster in gas. It takes 3, 4, 5 years. But nuclear, at least it takes another 10 years to recoup the initial investment. So it's pretty high. But again, nuclear power plants, the fuel is cheaper and the operational cost is a little lower. And hydro is the same. It takes a lot of time. It has a lot of environmental impact. That's the reason there's a lot of red taping and policy, which takes a lot of time. And on top of that, again, you don't know if you're going to have a rainy season or you're going to have a dry season. You don't know exactly how much water you're going to have. Another problem with hydro system is that you can't leave the dam open all the time. It's going to just empty the dam, or you're going to damage the downstream. So you can only get the energy when you need it from a hydropower system. Nuclear has the opposite thing. You can't turn off nuclear. It's not like a switch. Turning it on and off, it's a very dedicated process. That's why the nuclear power plants are, running 24/7. Maybe they will shut them down every 3-4 years for maintenance or something like that, or refueling. Once a year for refueling, maybe. So the cost of generation, we usually measure the megawatt hour, can vary widely. Another option is wind and solar. The initial cost for those is higher, but again, you don't have any operational costs because it doesn't require any fuel. And one thing to keep in mind is depending on the power plant that you use, some power plants use coal, some oil, gas. And in oil and gas, there's a term they say that having an oil contract is like being in a relationship, having a girlfriend or boyfriend. You can just, switch. But getting into a gas contract is like being in a marriage. It's at least a 10-year because the infrastructure, you have to lay down pipes. No one's going to lay down pipes to sell you gas for 3-4 months. Okay, so that's the reason it's a long-term commitment, and there's a fixed price usually for the next 10, 20 years. The price of gas has increased in the recent years because of the geopolitical influences, and the demand has gone up. So it's a little relatively cheaper than the alternatives, but with the rise of AI, you see a lot of these AI data centers, like the latest one that xAI built. They were forced to build a gas power plant just to supply that, and it was like a 400 megawatt gas power plant, for example. They put multiple, generators to just be able to run that power plant. So there is a, significant increase in demand in gas power plants, generators. So I know you work in this field, there's a, good job opportunity in that field as well. For these power plants that you can run in a day, just install and keep it running. Before I continue, how many of you went to the job fair? Did you go to the job fair? No? Okay. So, for the reasons that mentioned, some power plants like hydro and nuclear, because it takes a long time, it's very difficult to quantify, and it's different from one region to another, depending on the policies and so on. For thermal units, it's much easier. You have the cost of fuel, the depreciation of equipment, and so on, and you can relatively easily find the cost. Now, economic dispatch determines the least cost dispatch of generation for an area. For a lossless system, the ED occurs when all the generators have equal marginal cost. So this is marginal cost of each generator, 1, 2, 3 until generator M, which usually doesn't happen. I get an average of that. Now, for power transaction, these are contracts between areas to do power transactions. It could be between ERCOT, for example, east and west, or EXO and ERCOT or something like that, or Texas, interconnection. So between different areas, or it could be inside a city. Houston, for example, they have APNG, they have CenterPoint Energy, different companies that share power. These contracts can be for any amount of time at any price for any amount of power. The scheduled power transactions are implemented by modifying the area ACE, and its ACE is going to be equal to the actual tie flow power minus the scheduled one. Now, keep in mind some areas like Amarillo, because this has a monopoly, Xcel Energy, the price is capped and determined. They have a cost plus model, meaning they would calculate how much it costs to produce that power and put like 20-15% profit margin on top of that. But on areas, sometimes there's competition, so on. Now this model shows a 100 megawatt transaction, and so imagine if bus number 2 and bus number 1 are in the same city, for example. It's even better if I could put it on slideshow. So yeah, so bus number 1 is in a different area. You can imagine if bus number 1 is in Lubbock and bus number 2 is in 2 and 3 are in Amarillo. Let me see if I can bring up my pointer. Just give me a second. So imagine this is in Amarillo, this is in Lubbock, and they share power together. Amarillo is generating more power than it needs, so it could share some of the power to Lubbock, for example. Now, this is a scheduled 100 megawatt transaction from left to right. You have 8 megawatts from the upper transmission line going in and 92 from the lower one. But if you look closely here, you can see that this bus is actually generating 93 megawatts, but it's giving 92 megawatts to bus number one. What happened to to 1 megawatt? Why are these different? Yes, because of the losses. And what are these losses in a transmission in a real power? Are they inductive, resistive? They're resistive because these are real power loss. And the same thing you can see in the reactive power. This is negative 25 megavolt reactive, and that one is 30 megavolt reactive. Again, you have these reactive power losses, which is because of the transmission lines, and that's much higher than the real power loss usually. So,
is it called megavolt reactive instead of bars? It's volts.
So here we just are measuring the voltage, the reactive voltage that we have.
Instead of reactive.
Yeah, this is the way the software shows. Some of them actually I've seen they show it in VAR, but this one is the way that this one is it's showing. But that's a good question. Let me research this one and see, and I'll get back to you on this. Maybe it's the same thing, but it's just shorten it because sometimes these softwares do that. But thank you so much for bringing that up. Now, from bus number 3 to bus number 2, bus number 3 is actually supplying power to bus number 2, so you can see the direction of the flow. And again, here we have 85 megawatts produced, and this one is taking 84 megawatts. Now, how much is bus number 2 producing on its own? It's producing 150. How much is it consuming? 225. How much does it need? 75 megawatts. Yes? Am I correct? So it's getting 84 of that here, but again, from that, it's giving away 8 megawatts. So 84 minus 8, it's going to be what? 76. What happened to the 1 megawatt?
Lost.
Rest, yes, exactly. It's again loss in the system that we have. And the same thing on the right as well. The bus on the right, how much power is it consuming? A 100 megawatts. Yes, that's the reason we call it a scheduled 100 megawatt, because we need a bus that it's consuming 100 megawatts, but how much is it producing? 0. Okay, the generator for some reason, maintenance or something, is shut down, and therefore we need to import 100 megawatts.
Say that it's generating 32 mega
Volt amp reactive. Why are we doing that? Do you don't know? It's not generating, actually, it's consuming that much. And the positive negative means it's if we have a leading power factor or over a lagging one. The generator itself, it's a big coil. You have the transformers and so on, and that's a lot of it makes it very complicated, So again, the direction of the flows are shown with these arrows. The circle shows generation. These arrows at the end shows the load itself. And again, we're not interested in the reactive power here. We want to see how much real power are we getting. And that's the reason we are scheduled 100 megawatts. We are not mentioning the reactive power because, again, we were going to have power factor correctors at each end to correct all of that. We want to see how much real power, how much useful power we can, transfer. So, and in the exam as well, we're going to just focus on the real power part because we want to know how much work we're going to do with that real power. Now, for this particular one, we may not have any problems, but sometimes we have some constraints on the system, meaning the line is not able to handle like 100 megawatt power passing through it. You're going to damage the transformers, the transmission lines, sagging, are going to cause a lot of problems. So it's not like that, oh, bus one, I need 200 megawatts and we're going to flip a switch and give it to him. It's not going to work that way. We have to be able to delicately, be able to calibrate and send the power in a way that doesn't damage the system. Sometimes you're not able to give them the full power that they need. That's where the security constraint, ED, comes in. Transmission constraints often limit system economics. Such limits require constrained dispatch in order to maintain system security. In 3-bus case, the generation at bus 3 must be constrained to avoid overloading the line from bus 2 to bus 3. So, for example, here you can see that our system has now, when you are transferring from bus 3 to bus 2, you can see that it's reached its limit. It's at 100% capacity. And if you put more, you're going to damage the system. What you're going to do is to dispatch power for somewhere else. Perfect. So here dispatch is no longer optimal due to need to keep line from bus 2 to bus 3 from overloading. Even 100% is too much. You have to, optimal is to keep it around 80%, because 100% for 2-3 hours is going to damage the system. So what we want to do, instead of sending all the power, through bus 3 to bus 2, is to route that power through bus 1 and then bus 2. So you will send more power to bus 1 and the excess power will go to bus 2. But it's not that easy. Sometimes you don't have enough power to give to bus 1. You know what? And bus 1 is consuming too much power. It needs power for 2. So you have to be able to schedule that, and it's going to be difficult. That's the reason maintenance, shutting down a power file, it's done carefully when you want to do it. Usually they do it at midnight, after midnight for a gas turbine, because it takes like a few hours to kick back in. Sometimes it takes 24 hours. So you don't want to put pressure on the grid at the peak hours. You want to do it at off-peak hours. Now, to address the issue of overloading the transmission, if areas have direct interconnection, we use multi-area operations. So if area have direct interconnection, then they may directly transact up the capacity of their tie lines. Actual power flows through the entire network according to the impedance of the transformer lines. Again, actual power flows through the entire network according to the impedance of the transmission lines. The impedance, again, is the limiting factor. Flow through other areas is known as parallel path or loop flows. As mentioned, instead of having that, you can have another path going through. So now this shows a 7-bus system. It's just much more complicated. You have bus number 1, 2, 3. Oh, by the way, 1, 2, 3. I don't know if you see my pen. 4, 5, 6, and 7 bus. And they are in different areas. Bus number 6 is in the left area coast. Bus number 7 is in right area coast. I'm sorry. And case, I can't see it, it's too small. Case hourly cost is the upper one as well. And each area, again, this could be in different cities, different areas as well. Or even within a city. Now, you can see that each area, the cost is different. For the left area, it's $4,189 per megawatt hour. For the right area, the cost is $4,715. per megawatt hour, and for the hourly one, it's 16,933 megawatts per hour. And you can see the difference are much higher. The reason that a hourly cost system is higher because those usually require to, turning on these generators, which cost much more. And then you have the top area cost, which is $8,029 per megawatt hour. So system has 3 areas. The top area has 5 bus. Left area has 1, and the right one has also 1 bus. Now we can simplify it in this triangle. We have the top, left, and right one. And if we calculate the amount of power that they are sharing and dispatching, we get to this. The top is giving around 40 megawatts to the left. So system has 40 megawatts of loop flow. And left is giving another 40 megawatts to right. And right is giving around 40 megawatts to top. So you can see that the actual flow between areas is going to be about 40.1, which is, and the scheduled flow was 0. So there's a problem with this. When you have loop flow, you're going to have loss in the transmission. And by the way, this may seem like a small area. It could be between East Coast, West Coast, or Quebec and thousands of miles, and you're going to have a lot of loss. But there's a benefit. The benefit is cost. You can see that left area price is lower than the right, and it's significantly lower than the top area, almost half. So there would be probably a lot of demand from the left and right to get power from the top. But again, you're going to have loss, and there are other constraints as well from the transmission line, which I would explain. And the reason could be for different factors. Maybe the left and right are in, Midwest. They have a lot of wind, cheap energy, for example, or gas. And the one on top would be New York City. It's going to be much more expensive. Or, the one on the right has a lot of rivers, hydro dams, and so on. So it's going to be much cheaper. It's the case in Canada. So interesting fact. Do you know why aluminum in Canada is cheaper than US? And why do we need to, why it's difficult for US companies to compete with Canadian? And they are like, one is in Michigan, the other one is on, other side of the border, like 20 miles away. And so with like putting tariffs and everything, so aluminum coming from Canada ends up cheaper, and the labor costs, tax, everything is almost the same. It's about energy. So technically what US is doing when they're importing aluminum is importing energy. Extracting aluminum, it's a very intensive, and power consuming process. And they have a dam that is producing 2 gigawatts or so. There's a documentary about that. If you want, I could share it. And that is in a remote area close to a mine that produces aluminum. And it's very expensive to, transmit that power. So what they do, they use the power from the dam, which is cheap, very cheap energy to actually produce aluminum and extract aluminum and produce that. The temperature should be around 2,000 degrees Fahrenheit. I think for each kilogram, it's like 2 megawatts, something like that. Very, ridiculous number of power. It requires a lot of power. So when you're saying that we are importing aluminum, it's technically you're importing energy. And it's the same for cement and a lot of these cases because they have abundant amount of energy, and they don't know what to do with it. It's in a remote area. They use it to be able to extract aluminum and so on. And the same thing for, if we want to give an example for the meat industry around Panhandle area. We have a lot of cattle, more than humans. I think it's 8 million. It's a ridiculous number. But we don't have enough corn. Why? Because corn requires a lot of water. And the area imports a lot of corn from the north, Kansas and Iowa. And what they are doing is technically we are importing water, technically it's importing water and then raising the cattle. It's the same thing it's going to be in this case as well. So depending on the area, you're going to have different powers and different pricing. Now, this shows a 100 megawatt transaction between left and right. And you can see using this transaction, it will decrease the loop flow. So if I have more power going from left to right, instead of 40, I have 100, then the total power that's been transferred between top and left, from the top to the left is going to decrease from 40 to around 4.8. And you can note that TOPS losses have increased from 7 to 9.44. And the reason that they want to do this is because we learned that the electricity from left was cheaper than getting it from the top. And it's very expensive from the left to get the electricity from top. So there would be an increased demand on getting the electricity from the places that are cheaper, okay? But that on its own, what happens is you're going to put a lot of pressure on the transmission lines that get the power from the cheaper generator market. Now, why do you think the loss goes up? So these transmission lines, we usually want to increase the voltage to its maximum. When you have a low voltage, low power going through them, just heating up the transmission line, it's going to create a lot of, loss. So it's like you have a 10-lane line and you're just using one lane. It's more beneficial when you use 6, 7, or 8 of them. It's going to be much more, efficient in doing that. And on top of that, what happens is when you put extra pressure between left and right, or over 100%, you're going to increase the loss over there as well. So you can see that the area loss here went to 4.34, and the area loss went to 9.44. Now that we learn about the transmissions, we learned that the pricing of electricity is not just only depending on the generator. It also depends on the transmission as well. Where do you get the power from? How far is it? How much capacity you have? So the cost to supply electricity to the bus is called the locational marginal price, or LMP. Presently, some electric markets post LMPs on their website. In an ideal electricity market with no transmission limitations, the LMPs are equal. Transmission constraints can segment a market, resulting in differing LMP. Determination of LMP requires the solution of on an optimal power flow. Now, this shows a system, the 3-base system, which we have ignored the overflow to maximize the profit and the amount of power we can use. The reason is we want to get a lower price. Now, the cost to produce power in bus number 1, the generation cost, how much is it? Can you find it? It's $10 per megawatt hours. And the one from bus 2, how much is it? Another $10 per megawatt hours. And from bus 3, it's 10 megawatt per hours. Now these 3, but there's a small, yeah. So if we want to reduce the power that we want to have, but the actual power, let me put something in parentheses. The actual power for generating 2 is not 10, it's actually $12 per megawatt hours. Okay, so the actual power for this to generate is $12 per megawatt hours. So it's better to get the power from the ones that, get the power at a cheaper source. So generation 2 cost is $12 per megawatt hour. So to eliminate the confusion, this is the power that we are giving to the consumer. So 12. Generation 1 cost is 10 per megawatt hours. So line from bus 1 to bus 3 is overloaded. Why? Because the cost that we have for line, it's cheaper, and we want to get a cheaper power from line 1 instead of getting it for line 2. So if I want to get power, by the way, in this case, previous case, line 1 didn't produce any power. In this case, line 3 doesn't produce any power. So it has to import all the power from bus 1 and bus 2. Is it clear? So bus 3 here is not producing any power. It's producing 0 megawatts. Down here, it's producing 0 megawatts. That one is not producing as well. Yes, almost it's 0. So where does, and I'm going to explain that one. So where does the power, but it's not consuming anything as well. So the production is 0 in bus 2 and consumption is 0. But bus 3 is producing 0, but it's consuming 180 megawatts. Okay. Now, imagine we have 3 players. Okay, let's put it this way, or 3 producers. If I want to get, or this, let's say, I'm sorry, this way. I have 1 producer and I have 3 distributors. Let's put it this way. I have 1 producer and 3 distributors. You're going shopping on Amazon, eBay, okay, and finding your local store, Walmart, for example. Amazon, eBay, and Walmart, or Amazon and eBay. Amazon is producer and it's the seller, okay, and the product is Amazon Basic, and eBay is just reselling the Amazon product. To resell the Amazon product, it must make a profit. So it buys it for $10. It adds another $2 to it and sells it to you for $12. Okay. Both of them have warehouses. You need 1,000 of them and you need it tomorrow. You contact Amazon and you say, okay, I need 1,000. And they say, unfortunately, we can't ship 1,000. We can ship 100. So what are you going to do? You need to buy the rest from eBay, from eBay's warehouse. But eBay's warehouse is more expensive. It's $12. So you have to pay the difference. Does it make sense? So in an ideal situation, if I had enough shipping capacity, I would buy everything from Amazon and my cost would be $1,800. Where did I get this cost? Yes, I have 180 megawatts times $10 per megawatt hour results in 1,800. So this is the optimal situation. But this situation has a problem. It overloads our transmission to 120%. Okay? So no way we can ship this. We have to ship. So the other way is just to buy like 80% from this vendor, the other 80% from the other vendor, and we end up with this. Okay? So we buy 800 units from Amazon directly, and we buy the other 200 from eBay. It's the same, it's exactly the same product, but now I'm, rerouting the system. Now my cost goes to 1,921. Where did we get this number? Yes, combined cost of this, 180 on the amount that I get 100 megawatts from this one and 80 megawatts from this one. So 80 megawatts is at $12 per megawatt hour. So it's going to be 900 and how much? Anyway, 960, something like that. And I get 100 from 180, 100 megawatts at the other price. So for example, here it's like 14 megawatts per hour. Cost went up, or 10 megawatt per hour. And then suddenly I get to this price that I have here, which is a higher price, average price. And on top of that, the reason the price is a little higher is that when you buy it, so this is the interesting part. When Xcel sells you energy, okay, do they calculate the amount of energy that they are producing or the amount that you're consuming? So they have a meter over there as well, but they charge you based on what you have consumed. And there's a loss between there as well. So sometimes when you have long transmissions, they would add that loss to the system as well. Sometimes if you have reactive power loss, they would add that depending on how they work and operate. So you can see that line 1 to C is to 3 is, or A to C, I did it that way, is no longer overloaded, but now the marginal cost of electricity at 3 is around 14 megawatt per hour. So it's going to be higher. Now, this may seem a little complicated, and this is just 3 bus. Imagine if you have 2,000 bus systems, it's going to be very, very complicated. This is when these sophisticated softwares come in, and they are able to manage the system, reroute, loop the power, and redirect the power flow in real time. And some of them are able to optimize the costs. So if, for example, they will calculate and see if it's cheaper to run a diesel generator or is it cheaper to buy electricity from the neighboring state. And they do that carefully, and they have very sophisticated software to automatically do that. Yep. I think that's it for the last slide. Again, I'll post an announcement about your upcoming exam. By the way, I've posted the homework. Have you seen the homework? The quiz? I'm sorry, for the online students, the quiz. You have until this Monday to complete and yeah, I've already did that. I'm gonna post the second homeworks as well. This weekend you're gonna have. Did you all turn in the complex number? Okay, so I will post the second homework as well this week. And for the online students, I've already posted the quiz, and your exam is gonna be the first or second week of March. And I'll have a review session before that. Thank you so much. I think I don't have time to start the next slide, so I'll see you on Wednesday. Thank you.